We are looking at the HP11N Trinity Corona notes, if you're looking at those and following along. But we're looking here at linear and tangential, and then relating it to rotational velocities. So linear or tangential velocity is how fast something is moving in a straight line, where rotational velocity is how quickly something is moving through an angle. What we're going to be doing here is we're going to be looking at how we can relate these linear, these tangential, and these rotational velocity quantities for an object. Now, the big things that we've already talked about on our best friends in terms of comparing linear and rotational values is the fact that when we are comparing them, we care about equations like S equals theta times R. Because remember, circumference equals 2 pi, that's one circle, times the radius of that circle. And that a linear velocity equals the angular velocity times the radius. If you are swinging a sword or a bat, the end of it that's farther away from where you're swinging it is going to be moving faster than what's close to your hands. And this same idea applies with acceleration, that a linear acceleration is larger the farther away you are from that pivot point. So these are the three equations we're going to be looking at here. And when we do this, we are just looking at how, if we have a rotating object, how we can convert that rotational speed or acceleration or distance into linear quantities here. So one way we're going to do this is we're going to be looking at a CD problem. The way CDs work is, you put a CD or a Blu-ray or whatever into your computer drive, your optical drive, and it actually has a laser there that flashes over little divots, little pips in your CD, which are essentially ones and zeros in binary, as the CD is spinning very, very fast. And this works for CDs. If you go back in time a little bit, it'll work for LPs and records. And even for your hard drives are spinning super fast, upwards of 7,200 revolutions per minute, or RPMs. So they're moving very quickly. And what we want to do here is just for a CD, we want to find how fast it has to be spinning angularly, or in a rotational metric. So we're looking for an angular speed here in omega. How fast does it have to speed to give a point on the CD a linear speed, v, of 1.25 meters per second. And remember, linear quantities are those meters per second we had in the year, where rotational quantities, we're just replacing meters with radians, so that'll be radians per second. And we're going to see how this changes based off of if the laser beam is 2.5 centimeters from the center of the disk and 6 centimeters from the center. So if we kind of draw ourselves a picture here. We'll do blue. We'll make this a Blu-ray. Here's the inner circle of a CD. Here's the outer circle of a CD. And what we're looking at here is just how things go whenever they're at 2.5 centimeters, and then whenever we're at maybe 6 centimeters out here on the edge of the disk. So to do this, if we look at what we have here, we have these radial distances. We know what our velocity wants to be. We want to set the velocity to 1.25. We're looking for omega. So going back to what we saw from our best friend and what we wrote just up here, since we're looking for velocities, we can use this equation but solve for omega here. If we solve that for omega, we find that omega is going to equal that velocity, that linear velocity, the tangential velocity, divided by that radial distance. So when we do this for part A, that angular velocity we find is going to be the 1.25 meters per second divided by the 2.5 centimeters, which is 0.025 meters. And we want those meters because now our meters are going to divide out. And what we find for our answer here, if we grab a calculator, is 1.25 divided by 0.025 equals We get a nice even number here, 50. And if we look at the units, our units look to be just nothing over seconds. But remember, radians aren't a physical unit, but they're a placeholder. So these are radians here. For part B, we do the same exact thing, but this time our radial distance has increased. So it's still going to be 1.25 meters per second divided by, and this is going to be 0.06 meters as we convert that. Now if we think about this just for a second, we're trying to keep the same linear speed, but we're out farther on the edge of the disk now. And we know that just if a CD is rotating, that edge of the disk always wants to be moving faster than the inside. So if the inside had to rotate at 50 radians per second to keep this 1.25, then at that original speed, that original angular speed, the outside was rotating faster. So our guess here is that this rotation should slow down to read the edge of the disk here. So if we do the 1.25 divided by 0.06, we get 20.83, which makes sense. As we moved outwards on the disk, we'll just say 8 radians per second. As we moved outwards on the disk, we didn't have to rotate the entire disk as fast because that outer edge is always moving faster than an inner edge. So to keep it at a constant linear speed of 1.25, our angular speed actually went down there. So that's how we can approach a problem just like this. It's not too crazy what's going on there, but they're just linear to angular conversions or angular to linear conversions depending on what you have and where you're going. So with that, you can move back and forth between these two quantities and you can look at a lot of different stuff.